There we go. I keep forgetting to stream to the YouTube side. It should start in a moment. Thank you, Tosh, for reminding me. So let me confirm that that has started first before I continue with the lecture. Yep, I can see it now. It's all good. Okay, thank you. All right, there we go. So getting back to the lecture, so right now what we want to do is to apply resolution, because if I can keep applying resolution and eventually end up with basically nothing in a disjunction, then we are basically arriving to a contradiction. And when we arrive to a contradiction, that means the proposed theorem is indeed a theorem. That is the whole point of using proof by contradiction. All right, so we are going to try to apply resolution in this case. And so when we are applying resolution, we are looking for a term that is non-negated on one side and negated on the other side. So we want to compare and match every single disjunctive term and see if we can find a pattern like that. So I usually do it in a systematic way. So I look at not P or R, and I'm looking for non-negated P in the other disjunctive terms, and none of them has a non-negated P. Then I look at R, and I look at a negated R on the other disjunctive terms, and none of them has a negated R. Then I move on to the next item. I already know there are no non-negated P's, but I might find a non-negated Q. Nope, no luck there. So now I move on to this one, which means I'm now looking for a non-negated t, but only this term now, because I have already matched them with these things. So a non-negated t is only, I'm trying to match only with terms that are after the not t, and definitely this is not a t. So now I have concluded that no resolution is possible at this point. And yet I have not arrived to a contradiction, and as a result, this proposed theorem, okay, let me point back to what I'm talking about. This particular phi is actually not a theorem. It is not implied by what is known to be true, which is represented by psi in this case. All right. So let me see if you guys have any questions. And Jonathan, you are unmuted on the server now. So I'm gonna let you guys think about this a little bit and see if you have any questions. Not sure whether you guys heard that popping sound that was coming from an acorn falling from the oak tree onto my roof, and it's doing this, I would say, every 2 minutes or so, for the entire day, including nights. All right, so looks like there are no questions. So now we're going to move on to the next example. So in the next example, we have a phi prime, which is another proposed theorem. And we want to know whether phi prime is a theorem or not. In other words, we want to find out if it is implied by what is known to be true, and we're using the same psi in this case. So just like with phi, we have to find the negated version of phi prime first, because the idea of proof by contradiction is you have to negate the theorem that you want to prove. So the negation of phi prime is right here. It is the negation of just P implies not Q. And the negation of P implies not Q is the negation of not P or not Q, because I usually convert the implication to a or first. And then we apply De Morgan's law. This is a negation on the outside of an or. So I distribute the negation to every component inside the original or, but then I have to remember to change the or into an and. And then I perform another simplification so that not P is just P, not Q is just Q. And then I form the quote-unquote super CNF, which is the conjunction between the CNF representing psi and the CNF representing not phi prime in this case. So the first part, these two terms, they're coming from psi, and then the last two terms, they're coming from not phi prime. So this time I'm going to go through the systematic way again. And in this case, I take it back. I wasn't very systematic in this case. What I did here is I use underline to identify what I can use for resolution. So here's a not p and here's a p. So they can resolve, and they resolve to just not q. Now it resolved to just not q because this p here has no other term. So you can basically say, okay, there are two ways to look at this. You can look at this p term here as, oh, this is just p or nothing. That's one way to look at it, and that's why there's not q, because the other disjunctive term has only one single component in it. But the better way to look at this is to look at p as, oh, this is really just p or false, okay? Because you can always add or false to any expression, and it doesn't change the meaning of that expression. So if this is p or false, and this is not p or not q, then the concatenation after you apply the resolution rule becomes not q or false. Not q or false is just q itself. Not q or false is just not q itself, and that's why we can just write it like this. Now that we have not q as one of the terms of the entire expression, this q now has something to resolve with. So when these two resolve, it becomes it resolves to the expression of just false. And because this false is a component of the overall conjunction, so now the entire conjunction is false, and therefore we have our contradiction. P and not. So okay, so Jonathan is correct. Q and not Q is false, but that is not how we arrive to this false here. We're using resolution. So in other words, we don't use any special rules. We only apply resolution. And that's how powerful resolution is. So if there are any questions about this step, I know this may look confusing. So let me just go ahead and use the tablet to do the derivation by hand, just so that it becomes a little bit more clear. But before I do that, I'm going to copy the expression so far onto my tablet. And you guys can go ahead and ask questions in the text channel, so I am still keeping track of that. Okay. All right. So we got a question in the text channel. I was going to ask if you could do a derivation by hand. So I am doing this sort of by hand, but it's the same problem. So let me move the tablet screen to be captured like this. Okay. All right, so this is copied from the example itself where we only have p and q by themselves, and that is coming from not phi prime. So, but what we can do here is we can say, hey, if it's just p, it really is the same thing as p or false. You can always add a or false in any disjunction because it doesn't change the value of the original one. So now what we're going to do is we're going to try to resolve. So when we resolve, we see that there's a negation of p over here, and there's a non-negated p over here, which means now we can apply resolution to these two specific disjunctions. Now, if you have not reviewed the concept of resolution, or what the mechanism is, how it works, it's probably a good time to review it after today's class, okay? Because it is very important that you understand the mechanism itself. But the mechanism is basically a concatenation operation where p and also not p, they disappear from the concatenation. So as a result of this, I'm going to be a little bit lazy and try to copy and paste as much as I can. Okay, so we got that. Duplicate and paste over here. Ah, that's excellent. I end up actually just copying everything that I need. So now we can add a new term because everything that is implied by what the expression already has can be concatenated using an and without affecting the meaning of something that we have already derived. Okay, and I'll prove that in just a little bit. So in this case, we can now say, oh, okay, so we have a new term here, which has not q on one side, and then we have false on the other side. P, not P, they do not appear anymore, and that is the whole point. That's the power of resolution. It can remove one variable by each application of resolution. So now we look at this new thing here, and then we say, hey, there's a Q over here, and there's a not Q over here. They can resolve, right? So I just go ahead and underline this, and underline this to remind myself, which two things are being used for the resolution. So now the new expression is becoming longer, but this is the last revision of the entire thing. So let me select the whole thing, copy, and I guess paste over here. There we go. And that's a good place for it. All right. So now we can say, let's add the result of the resolution, and the result of the resolution is now false or false. The first false is coming from here, the second false is coming from here, but that's really kind of redundant because false or false is just false. So now, this entire thing becomes blah 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 and false, and this is where we can make that conclusion that the entire thing is false. So we can now say this entire thing is false, and now we have our contradiction. And with that contradiction, we can now conclude that the original phi prime is indeed a theorem. That is how we apply all of the things that we have learned so far into this one single example. So I want to see if you guys have any questions at this point, because I have just completed one example of how to use resolution. Okay, all right. So some people are making sense out of this whole thing. It's a little bit complicated because there are a lot of components, a lot of conceptual components to get to this point. Alright, so we got a comment in the text channel. Yeah, I'll need to review resolution just a little, but the application makes sense. Yeah, resolution is basically just saying, it's kind of like making a new molecule out of two smaller molecules, right? Except in this case, in order for the two smaller molecules to make the bigger molecule, one of the component of one molecule has to be the negative version of something, whereas the other one has to have the non-negative version of the same thing. And when you connect the two molecules, you lose this little molecule or this component where it is negated on one side and not negated on the other side. So that's kind of one way to look at resolution, is you're making a new compound, except the new compound has one fewer component compared to the sum of the two components that you're combining. It's not quite like sharing electrons because it actually went away. We lost one component when we combined the two. So when you look at it, like right here, so when we look at this as one molecule and when we look at this as one molecule, when we combine those two, Q, not Q are lost, and all we have left are the remaining portions of it. Yeah, it's kind of like annihilation, but it's not exactly that. All right, so what I'm going to do is I'm going to give you a very quick and brief overview of what we have, what led to this point. Okay, so what led to this point would be, initially we talked about proposition calculus, which is only describing a fairly mechanical and syntactic process, and say that, hey, if you can match, all the patterns in this particular set on the left-hand side of the inference rule, then we can mark what is on the right-hand side of the inference rule to be true too. So look at everything that is true, that is marked true up to this point. Not just things from the iota, but everything that is marked up to this point. Look at all of those things and see if you can match the pattern that is described by the set on the left-hand side of the inference. So this is inference, and the left-hand side of the inference is a set. And in the set, you can have multiple expressions, multiple well-formed formulae, and those will be the ones referring to the Greek letters. And then each Greek letter is representing a well-formed formula by itself. And then whatever is on the right-hand side of the inference is another expression that involves the same Greek letters, and that is the new well-formed formula that can also be marked true. When you have all of these things already known to be true, then this thing will also be marked to be true. So that is the basis of the mechanism. It's a very syntactic or mechanical process to mark more and more and more well-formed formulae to be true. And in the original propositional calculus system, we have the zeta set, okay, consisting of a whole bunch of rules, okay. Every rule looks like, a set of some kind infers, another expression over here, another set infers some other expression over here, and so on. And it is a pretty large set because we have basically the number of items in zeta will be the number of Boolean algebra rules that we understand. So there's a whole bunch. And what is even more alarming is when we look at the set of all the well-formed formulae, it's an infinite set. It's a set with infinite number of items. Okay, so if you want to prove something, we have a problem because we cannot distinguish between the condition of 1, what is being proposed as a theorem is really not a theorem, or the fact that we have not been able to label it yet as a well-formed formulae that should be marked as true. So we cannot distinguish between those two because you are being asked to find possibly a needle in an infinitely large haystack. You cannot make a conclusion because, one, you don't know whether there's really a needle in a haystack or not, or just that you have not found it. But because your haystack is infinitely large, there's no easy way to tell which case it is. So that's basically the problem of the original propositional calculus system. So what we have done so far, okay, is to change things a little bit. And by means of changing things a little bit is in omega, we only have two symbols left, or two connectors left, or two operators left. One is just negation, and the other one is or. The rest are all gone. Okay, and then we have to redefine what is well-formed. So a well-formed formula, in this case, in general, if I want to display in the graphical sense, it's going to be a bunch of a disjunctive term and another disjunctive term and another disjunctive term and another disjunctive term and so on. Then the question is, what can we have as components of the disjunctions? Each item here, here, they can only be things from alpha. They can either be a non-negated item from alpha, or it can be a negated item from alpha. But nonetheless, it cannot be anything else. In other words, we have a restriction of what we can apply the negation symbol to. It can only be applied to a symbol coming straight out of alpha. Negation can no longer be applied to an expression itself, other than a very simple item that is coming from alpha. So we tweaked the rules a little bit, and then the most significant portion of the tweaks is the way we handle zeta. So zeta, which consists of all the inference rules, used to have a lot of items. It's not infinite, but nonetheless, there are a lot of items in it. But now, there's only one item. And that one single item looks like this. Okay, so I may not be using the Greek symbols, consistently, but the idea is still the same. So we have psi or phi on one side, and then we have not phi or rho on the other side. And what we can infer from these is an expression that only has psi or rho in it, and that becomes the only rule that we need. Oh, okay, I take it back. That's supposed to be a psi, not a phi. This is a psi. There we go. So we only got one rule left. Okay, and what about the problem of, it's an infinitely large haystack and we may or may not have a needle in it? Well, as it turns out, when this is how we define well-formed formulae, the space of well-formed formula is the space of well-formed formulae, that should be plural, is going to be finite. Okay, think about it. Actually, I make a mistake here. Let me correct my mistake. Conjunction is not an operator, right? So well-formed formula can only look like this. That's all. Okay. So now the question is, how can we be so sure that the space of well-formed formula, the space of well-formed formulae is finite? Well, the number of symbols in alpha is finite, especially when we are considering just the variables. Okay, so let's consider the case where we have 5 variables. So we have p, q, r, s, t as our variables. The Greek letters are not really used as variables, they're used as placeholders for an expression. But in this case, each placeholder has to be a variable, but nonetheless, it is still a placeholder, and that's why we use the Greek letters for that purpose. The variables, on the other hand, are the English alphabet letters. So in this case, we have 5. So if you think about a OR expression, that can involve either the negated or the non-negated version of a variable, or it's completely missing a particular variable. How many of those expressions can we have? Does everybody understand my question? Let me restate the question that I'm asking, because I want you guys to think about it. Okay? So each disjunctive expression can consist of a disjunction of the following. Each item can be a non-negated PQRST or a negated PQRST. And we only have 5 variables in this case. So the question is, how many disjunctive expressions can I make based on this particular restriction? So I'll let you guys think about it a little bit. And the way to think about it is like this. Okay, so you look at P, Q, R, S, T, and then you look at each expression and say, what are the possibilities revolving around P? Okay, so we can have P unnegated, we can have not P, and we can also have nothing here. P is not even mentioned in this disjunction. Those are the only 3 options available to variable P, or how it appears in a disjunction. Is that okay? Does everybody understand why we only have these 3 options for this specific variable P in any well-formed formula in this particular space? Okay, so we got a yes. What about the rest of the class? Are we good to go, or do you guys need more time to think about this? Okay, so we got 2. All right. So when it comes to Q, it's the same thing. Every disjunctive element can only have Q, not Q, or missing Q entirely. And the same thing for R, and the same thing for S, and the same thing for T. So that means there are 3 options for P, and independent to which option we choose for P, there are 3 options for Q, and independent to both how we choose which option of P and which option of Q, 3 over here, 3 over here, 3 over here. So when you multiply all of these, Then you have a finite number. This becomes an upper bound of the number of expressions you can make based on all the restrictions that we have. So this is basically 3 to the power of 5. Now 3 to the power of 5 is it's a little large, but it's not really that bad, right? Because 3 squared is 9, 9 squared is 81, 81 times 3 is what? 273. So that means when we look at the cardinality of the set consisting with all the well-formed formulae, there are only 273 items in it, which is not too bad. And somebody's going to point out, but Tag, this is as you increase the number of variables, the number of items in the set will also increase. That is absolutely true. And it's not a very nice curve either, because this is exponential. Because if n is the number of variables, then the number of items in that particular set, the set of all the well-formed formulae, is going to be 3 to the power of n. Nonetheless, it is finite. Okay, that's the best part of it, is it is still finite. And then Jonathan asked why it is to the power of 5 rather than times 5. Okay, I can explain that. So the best way to explain that is to use a tree to explain it. So we can always say that the false is always a mandatory item, even though most of the time we don't write it, because otherwise we'll be writing a lot of or false, or false, or false in every single disjunction. So, but it's a mandatory item in the whole thing. So now when we try to explain what the three options for P, we can have P non-negated, we can have P negated, or we can have P entirely missing. Okay, so what if P is non-negated? Then we get to choose Q. So now we can say Q has three options too. Q, not Q, or Q is missing entirely. Okay, I made a mistake here. This is supposed to be not P. So what if we choose not P to begin with? Well, it doesn't change what options we have for Q. So Q has Q, not Q, and missing entirely. What if P is missing entirely? Well, guess what? It doesn't matter when we get to Q, because we still have the same three options for Q. And it is time to take row. So I'm going to switch around to row taking here. Let's see, where is... Yep, right here. Leave student view and get to row taking for today. And I'm showing you the answer first, so I can copy and paste it to the text channel. And this time it's not very funny, it's not very inventive, it's just C and F, conjunctive normal form. Paste it into the text channel. And now we can save and publish, and you guys can go ahead and copy and paste C and F as the answer. It has to be all uppercase. So there you go. So as you guys are doing that, I'm going to go back to the tablet and just add a few more levels to it. Okay, so we'll go ahead. I'm going ahead to kind of make this picture a little bit more complete. So when it comes to R, okay, it has 3, 3, 3, 3, 3, 3, 3, 3, 3. And obviously when it comes to S, it's the same thing. So this is a very interesting way to visualize why it is 3 to the power of 5. Because every level along this tree is multiplying the number of nodes of the previous level, of the parent level of that particular node. So if you have 5 variables, then you will end up with 3 to the power of 5 leaves by the time you get to the end of this entire tree. So let me know whether this is helping or not. Jonathan has already said yes, but I want to check with the rest of the class and see if it is making any sense to you. And this is also why CISP430 is a co-requisite of this class, because they introduced the data structure tree in the class CISP430. And I mean, the concept of a tree is not really that difficult to understand because we deal with trees all day long. When you look at the file system, how a folder can contain other folders and folders can contain files and so on, that is a tree already. But in terms of a more formal treatment of what a tree is and how to analyze the number of nodes in a tree, then CISP430 is a helpful class to have. And that's why it's a co-requisite. Alrighty. And I'm going to assume that most of you are done with the road taking activity. Oh, it has not been introduced yet? Okay, I guess it depends on who's teaching it and the pace of teaching that class. That's a pretty intense class too, CISP 430, but in a different way. CISP 430 is a programming class, but this class is not really so much a programming class. All right, so we got 2 people typing, and I'm gonna wait until I see what they're typing. I see. Okay, so it'll be introduced in 2 weeks. Okay. Well, there are trees and then there are trees. Okay, there are some trees that are really simple and to understand and construct, and then there are trees that are really difficult to handle. The self-balancing trees, for instance, those are much more complex compared to, let's say, a binary search tree. So, oh, okay. Well, um, I believe I have taken up to 3 programming class, 3 computer science classes in 1 semester. Yeah, so if you okay, so this is the trick that I used when I was a not grad student, but undergrad student. I try my best to correlate between different classes. So I look at the concepts of one class and then I ask the question, not only how is this relating to other material, other concepts of the same class, but also how it relates to concepts from other classes. And the moment you start to do something like this, to look at the correlation of concepts between classes, then it is possible that you're taking actually 3 classes, but the actual effort that you have to put into it is maybe 2 classes or even 1.5 classes. It all depends on whether those classes have a lot of a relationship or not, but it is possible. All right, I'm glad that Wade has already learned this trick. To me, it is not a trick to learn. That's naturally how my brain works. It just naturally looks for things that are related, and it just spots those things without me actually having to think and go like, "Hey, these things are related." That's also a trait of my personality type, which is INTP. All right, so um, continuing on to the quick review and summary of what led to this point. Okay, so we got omega taken care of. We only got 2 things left, and there are very strict restrictions as well as to what we can apply a negation to, and then well-formed formulae. Okay, that's pretty easy. We can only have disjunctions, and within the disjunctions, each item can only be a symbol from alpha or the negated version of a symbol from alpha. And then zeta is even better, okay? Instead of all of those other rules, okay, the identity rules, De Morgan's law, distribution, blah 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 blah. Instead of having all of those different things that you have to choose from, guess what? You got one rule now, just one. You don't have to choose, okay? What you do have to choose is which 2 disjunctive term do you want to use as these 2 in order to label a new well-formed formula to be true. Okay, you get to choose over there, but you can do it in a very systematic way. So these are all good, right? And then oh, ENTP. Yeah, ENTPs are the more extroverted versions of INTP. I mean, there are other differences as well, but ENTPs and INTPs typically would behave in certain ways, very similarly. And so are INTJs. INTJs and INTPs can appear similar on the outside, but inside is entirely different. It's kind of like the old Volkswagen Bug versus the new Volkswagen Beetle. On the outside, the styling is very similar. And then you open the hood, then you go like, what the? Because, okay, for those who are not understanding my analogy, the original Volkswagen Bug is a rear engine, rear wheel drive kind of vehicle. So the trunk is actually at the front. The new Volkswagen Beetle is basically just a restyled Golf. The engine is in the front and it's also front wheel drive. It has a very tiny little space in the trunk, but it's just the styling, okay? So internally entirely different cars, but externally they look similar. So that's the I'm getting into the MBTI, stuff, so I digressed, which is also something that ENTPs and INTPs are very good at, is getting distracted. We like shiny objects. All right. Yeah, those personality type things, it's very interesting because depending on your personality type, it also can affect, what is the most effective way for people to study. And so, if you are trying to look into the best way to study, whether to study with somebody else, whether you want to do hands-on exercise when you're studying, whether you need a quiet environment, or whether you like to study when you're at a coffee shop, those actually relate to your personality type. So it's really quite interesting. Quite interesting. All right. So moving on, there. Let's see. One more thing that we need. So that is proof by contradiction. So proof by contradiction is the next piece. So proof by contradiction is the fact that if you have psi representing everything that is known to be true, so the way I make my psi in theory is going to be a conjunction of everything in iota, and we are just making a big old gigantic conjunction out of all the expressions from iota. That is our theoretical side, which is everything that is known to be true. And then we have a proposed theorem, and I'm going to call that phi. So phi is a proposed theorem which can be anything, right? So I lied a little bit earlier. I said there's only one more thing to do, which is proof by contradiction. That is not true, because there's also the concept of a CNF, okay? So phi can be anything, can be any general Boolean expression, but using the completeness of CNF, we can now say, hey, going through Boolean algebra, we can turn this into a CNF, and that would be not phi itself, but the negation of phi. Because in proof by contradiction, you need to first negate the proposed theorem before you make a conjunction between what is known to be true and the negated theorem. But the negated theorem can turn into a CNF. We know that CNF can be used to represent any general Boolean expression, and that is really important. So now, the final piece is we have psi, and then we make a conjunction of the CNF that is representing not phi, and then we apply resolution, and then we ask the question, can we resolve to false? So this is phi, this is false, okay? So we are asking the question, after the applying resolution again and again and again and again, every single time we apply resolution, we are losing one variable joining the rest of the two disjunctions that we started with. So hopefully, eventually, we'll get to false. If we indeed get to false, then we can use proof by contradiction to say that the original phi, not the negation of phi, but the original phi is indeed a theorem. On the other hand, if we get to a dead end, where there are no further resolution to apply, and yet we do not have false as the result of resolution, then we can basically say, well, the original phi is not a theorem of psi. In other words, it is not implied by psi. It does not mean that phi is false, okay? It simply means that it does not follow what is known to be true. Is that okay? Does everybody understand what I just said? Okay? There's a difference between this expression is not implied by those things over there, as opposed to this particular expression is not true. Does everybody see or understand the difference between those two concepts? Not. Okay, so Jonathan said not. Yeah, okay. So let me explain that a little bit. Yes, absolutely. Okay, so I'm going to give you an example. So I'll give you a statement that is known to be true. Okay, so the statement that is known to be true is, okay, after a boring class, people feel refreshed because they fall asleep in a boring class. Trust me, I have done my own sleeping in class during my college years. Sometimes I would fall asleep in a 2-hour class 15 minutes into the class. Not my proudest moment, but it does happen. That class turned out to be file structure. In other words, they talk about, okay, in order for a file to exist, you need this sector on a hard drive to represent all this information here. We allocate 2 bytes for this, 10 bytes for that, 255 bytes for this, and so on. So a lot of tiny little details, a lot of pine needles. So 15 minutes into the lecture, I would fall asleep. Now, the teaching style of the professor did not help. This particular professor has a habit of drawing circles, okay, and I can try to replicate it using the tablet. So he's prone to drawing circles on a projector. And we're talking about transparency projector. So basically, you slap a transparency sheet onto the surface, and which usually has printed material on it already. But when he uses his marker to draw big gigantic circles, we are looking at a gigantic hand going in circular motion. It is very hypnotic. It's extremely hypnotic, and he has this kind of really flat voice, and he has a mic to because he is very soft spoken with a very flat voice. So through the mic, it's kind of like the perfect environment to fall asleep. Really, it's kind of interesting. I passed that class, but it was I fell asleep a lot in that class. Anyway, distracted. I distracted myself. Sorry. Okay, so let's say this is a true statement. Okay, after a boring class, people feel refreshed. There we go. Back grammar there. All right, and so to show you what a theorem is, okay, we'll say tax classes are boring. All right, which probably is true for many people. And so, the conclusion, okay, the theorem, okay, that we are trying to prove here. So these two things are known to be true. In other words, these two would be your psi, okay. So what my phi is Jack, who is taking tax class, is refreshed after class. Okay? So that statement is actually a theorem in this particular case because it is logically following what is known to be true. So phi here is logically following what is known to be true. Is that okay? Does everybody understand logically how these two facts that is given to you is basically saying this has to be true? If after a boring class people feel refreshed is true, and tax classes are boring, if those two facts are known, then if we know that Jack is taking a class from tech, and then we know for sure that he's going to feel refreshed after the class, right? Okay, so in this case, there's an implication here. Logically, one is following the other. Now, I can also give you a statement that may be true, but it does not follow what is known to be true. Okay, so now we can say Mohammed is taking a class from Iraj, and he feels refreshed after class. Okay, we'll call this row. Okay, so row is a statement. It can be true, it can be false. Okay, no, I didn't say whether it's true or false, but it certainly can be true, but it is not logically following what is known to be true. Does that make sense? Okay, so we got one confirmation. So this is the difference between whether it's a theorem or whether it's just an expression, but it really has nothing to do with what is known to be true. Because Mohammed may feel refreshed after Iraj's class because Mohammed may have very good healthy habits, right? It can be because of other reasons, reasons other than Iraj is also a boring teacher. So that is the difference. Okay, so when you come up with the conclusion in the next exam, which is going to have something like this, I don't want to see people saying the proposed theorem is false, because it doesn't guarantee that it is false. What it guarantees is it is not logically following what is known to be true. So the best way to describe it is simply to say it is not a theorem. That's the best way to describe it. All right. So remember this example, when you have to make a conclusion after taking all the steps of resolution. All right. So the five components, okay, that we have talked about. One is propositional or proposition calculus, which is a mechanical system. You can kind of look at this as, oh, okay, this is a very mechanical process. Give me the ingredients and this machine will turn in a certain way. Okay, it's a very mechanical system. And then we have the concept of CNF. Okay, CNF plays a very important part because it is complete. Okay, we can turn any Boolean expression into a CNF. Okay, and then we talked about resolution. And resolution is also very important because resolution works on CNF. Okay, if you have an expression that is in the form of a CNF, resolution works on it very easily. Okay, so resolution is a mechanism that works on CNF. And CNF is complete, which means we can turn any Boolean expression or any collection of Boolean expression into a CNF. And then we have proof by contradiction. Proof by contradiction exploits the fact that when we apply resolution, we are losing terms. Okay, we are losing variables every single time we apply resolution. So hopefully, by repeatedly applying resolution, we'll get to a disjunctive term that has quote unquote nothing in it. But it's really not. It's not nothing because there's always a false inside a disjunction. So when we get to only the false, which is a constant, then we have a conjunction that has at least one component being false, and then the entire CNF is going to be false. And then we use proof by contradiction to say that okay, we have to negate the theorem first, but the negated theorem turned into a CNF and concatenated with the CNF representing everything known to be true. So with that long CNF, if we ever can use resolution to eventually get to a contradiction, then we have proven the proposed theorem to be a theorem. So that's how all of these different components interact with each other to come up with what I have just described. And this is a very mechanical way to prove theorems. And the reason why I talk about this, because most other professors teaching this class will teach you how we do things. Okay, the 20 gazillion elements inside zeta. I want to introduce this method because that's the whole purpose of trying to do this all of this stuff with computers, because we want the computer to be able to prove theorems in a very effective way, and this is kind of a way to do that. So I just want to give you guys a moment here to see if you have any questions about this quick summary of this entire module that talks about proposition calculus. And we have already talked about the relevancy of propositional calculus. Now, by itself, propositional calculus is not really that useful in computer science, but it does lay out the foundation of more complicated theorem proving mechanisms, and namely that would be predicate calculus. We probably should get to predicate calculus in this class, and if we do, we'll basically do a little bit of fun project using Prolog, which is a programming language. Well, okay, I should say programming language in quotes, because it is not a very conventional programming language, but it's a very fun, interesting programming language. It can do certain things very, very well, but it really sucks at doing some other things. So it's but by the time we get there, it'll be quite interesting. All right, I'm just taking a look at the time. We still got about 25 more minutes. So if we don't have any questions, I just want to remind people that the assignment is already out. Okay, so if you look up the assignment stuff, the CNF assignment has been assigned since Monday, and it is due next Monday. So you still got 5 days to work on it. Okay, and it's fairly mechanical. It's just turning expressions into CNF in this particular one. But I do recommend that you start early, because in case you run into problems, you can start to ask me about those questions. All right. I don't see any questions from Discord. All right, so now it's time to move on. So I'm just moving on to the next topic sequentially. So after propositional logic, we are now going to talk about discrete probability. So before we get into some really boring terminology stuff in counting, let's talk about the Lotto game. Okay, and specifically, let's go to, let's see, Super Lotto, I think. Super Lotto. And the first thing we want to do is to understand the rules. Okay, so we go to Cal Lottery. Now, it is really quite ironic that the money made from selling Lotto tickets is supposed to go into education. So this is a self-defeating mechanism. Why is it a self-defeating mechanism? Because the more educated people become, the more they understand probability and stuff like that, the less likely they're going to buy Lotto tickets, and the less and then the funding is going to dry up, right? So it's kind of a self-defeating mechanism. But once we lose all the money, into education, then people will not be as educated anymore. Then they will get to start to buy tickets again. Then we have money to improve education again. So the whole thing is going to be a pendulum swing, if my theory is right, which is usually not the case. All right, so now we're going to look into a specific game. I think Super Lotto is one of those, and we want to look at how to play. I mean, some of you probably know all this stuff already, but I'm not going to make any assumptions. So in Super Lotto, you can buy a Lotto ticket. What is in a Lotto ticket? Well, in a Lotto ticket, there are 5 numbers in it. The 5 numbers is going to be each one is from 1 to 47, but a number cannot repeat. Okay, so you have 5 unique numbers between 1 and 47. And then you have one extra number that is called the mega number. The mega number is from between 1 and 27. So on the Lotto ticket, you got 6 numbers, the mega number can actually repeat one of the five numbers that you have chosen. Um, so there's those two are independent. Okay, the first five numbers and the mega number are independent. All right, and then you pay $1 per play for each Super Lotto Plus ticket. Know the time Super Lotto Plus draws take place Wednesdays and Saturdays after the draw entry closes at 7:45 p.m. on the day of the draw. Remember that Super Lotto Plus has 9 winning ball combinations, blah blah blah. And so the question is, when is a good time to buy a Super Lotto ticket? So what are you going to use as a gauging mechanism of, should I buy a lotto ticket today? So what kind of information is going to help you make that determination? Okay, Jonathan has already made the conclusion it's never really a good time, but let's just say that you want to determine, okay, what factor, what kind of information do you use to determine whether it's a good time to buy a lotto ticket or not? The jackpot, right? I mean, how much is in the jackpot? And I'll later explain why even that is not a very useful information. But let's just say that we'll use that as an information. So now you want to look at the jackpot, the amount of the jackpot, and you want to look at the probability of the ticket or tickets that you purchase is going to be a winning ticket. Okay? Because if it does work out, okay, then it may worth that $1 to buy a ticket because the chances of winning the jackpot is is fixed. Okay, it's not actually fixed, but I'm going to make the assumption that it is fixed. And the jackpot is a certain amount, so on average, okay, whether you're going to lose that $1 entirely or whether you make some money because there's a chance of winning the jackpot, so you can actually calculate it out. So now the question is, how do you calculate it, right? So let me use my tablet because this is something that can be graphically displayed, which is really kind of cool. All right, so let's think about how the first five numbers are going to be chosen. Okay, so you might think, okay, this is going to be a gigantic tree because the first number can go from 1 to what? I can't remember the number. I think it's 47, but I can be wrong. 47, that's right. Okay, so the first one can be 1 to 47. And then the next number, okay, if the first one is 1 already, you cannot have another 1. So if the first number is a 1, then it only goes from 2 to 47. If the first number is a 2, then it can be 1. And then you skip 2 and then 3 all the way to 47 and so on. So in this specific case, I am looking at this where the ordering is important, where it is actually not important. We'll take care of that later on. Okay, so if ordering is important, then you have 57 choices, or excuse me, 47 choices at the first level of the tree. And then for each node of the first level, on the second level, you got 46 choices. And then the next one only got 45 choices, 44 choices, and then 43 choices. Does that make sense? Because a number a number cannot appear twice. So once you have used up a number, it is no longer a possible choice down the road. Okay, very good. So now we look at this and go like 47 times 46 times 45 times 44 times 43. And then the last number, the mega number, is independent, so that one has 27 choices out of it. So order does not matter, okay? But in this case, I'm counting as if order does matter. So how are we going to take care of this problem if order really does not matter? So what you need to do is to think about, okay, let's just say that we are looking at the five numbers of 1, 2, 3, 4, 5. So now you have to think about how many ways, how many different ways can I arrange 1, 2, 3, 4, 5? Okay? Does everybody understand what I mean by this? I have already chosen 5 numbers. I just want to know how many ways can I reorder these 5 things. So 1, 2, 3, 5, 4 is another way to arrange this, right? 1, 2, 4, 5, 3 is another way to arrange this. 1, 2, 4, 3, 5 is another way to arrange this. Blah, 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 blah. Okay? So the question is, how many different ways can I rearrange these 5 items? Well, that math turns out to be pretty easy to understand too, because if I just give you a bag of 5 items and I ask you how many different ways can I pull items out of this bag where ordering is important, then you go like, okay, well, the first item I pull out of the bag, there are 5 possibilities. After that, I have 4 possibilities, and then 3, and then 2, and then 1, and that turns out to be 120. 5 factorial, exactly, okay? But I'm going to introduce factorial in just a moment, maybe not even today. But the idea is, given that we have 5 unique items, there are 120 ways to arrange those 5 items around, okay? So that means I can now reverse the whole process and go like, hey, this number is representing the order dependent ways of taking 5 things out of 47, but since ordering is not important, that means I have to divide it by 120. Does that make sense? Alright? Okay. So when you look at this entire number, it would be the number of unique Lotto tickets that are possible. Okay? So that number turns out to be, okay, let me pull out a spreadsheet to figure this out. I mean, you guys can probably just use your own calculator, but I'm going to use a proper spreadsheet to do it, which is an overkill. There we go. Alright, so I'm just going to use my manual method to do this. 47 times 46 times 45 times 44 times 43. The whole thing divided by 120, and then multiply that by 27, and it becomes this number, which is what? I'm just counting the zeros. 41 million something. Okay, let me just turn on the formatting here, so it's easier to tell what quantity are we talking about here. So we go to format, number, and then we want the general format. Oh, I guess that doesn't work. Let's try that one more time. We want number format, and we want the comma. I think it's the second one. No, yeah, okay, that works. There we go. So it boils down to 41 million something, okay? So now you might think, if the jackpot is $42 million, then it's worth it to buy a lotto ticket, right? Because the chances of you winning the lotto is 1 in 41 million something. But if you do win, then you have a jackpot amount of $42 million. So you might think chances is on your side, right? It's worth it to buy that one lotto ticket. Unfortunately, the math doesn't quite work out that way, because you have to pay taxes, right? So how much tax do you think you have to pay if you choose to take in the entire jackpot in a lump sum? Let's just call half, okay? So that means you kind of have to take that into consideration, because your tax is going to be 50%. So now you say, okay, well, I just have to adjust my expectations a little bit, right? So I'm going to take the chances of winning and then multiply that by 1.5 to take into consideration that I have to pay taxes. Half the money is going to go into taxes, and actually, I take it wrong. This is the wrong number, because you have to multiply by 2, because half your money is going to be going into taxes. So if you want to break even, you need the jackpot to be 80, what, 82, 80, close to $83 million. Okay, so if the jackpot is indeed $83 million, is it worth it to buy that one lotto ticket? The question is no. It is still a no. And then you go like, why? Well, because the state can issue duplicate tickets. There's no guarantee that there's no restriction of the state can only has 41 million something unique tickets, and once those 41 million unique tickets are sold, then there will be no new tickets sold. There's no such rule. Okay, in other words, whenever somebody walks into a 7-Eleven and say, I want to buy lotto tickets, all of those lotto tickets are randomly generated on the fly, which also means you can sell, okay, the state can sell more than 41 million tickets to people. Then you end up with a duplicate. Several people can win the jackpot at the same time. So now the question becomes, depending on the jackpot, what are the chances that you will have several people winning the jackpot at the same time? So that is no longer something that we can work out using the math from this class, because now it's basically you're trying to model psychology, okay? Because you're basically trying to say, okay, how does the likelihood of people buying a ticket change when the jackpot changes? And that is something that I have no idea about. So but later on, we'll figure out a way to have some kind of a model. In other words, of all the past lotto sessions, okay, do we know how many tickets were sold, and do we know what the jackpot number is? And I think both of those are public information, so you can kind of make a plot of a curve, and then you can kind of project the curve and go like, okay, if there's a jackpot of $83 million, how many people would end up, have hitting the jackpot at the same time? I think historically, typically you have a lot of people, getting hitting the jackpot when the jackpot is high enough. So the conclusion, the fast and simple conclusion is, it's never a good time to buy a lotto ticket. Now, that is just my opinion. If you think, but tech, you're just trying to make sure that we do not become millionaires because we don't buy that one lotto ticket that I'm going to win and I'll be set for life, don't take my advice. Go ahead and buy your lotto ticket. Okay, don't let me stop you. I'm simply stating the fact that from the standpoint of statistics and probability, it's never a good time to buy a lotto ticket. That's all I'm saying. All right. So what we are getting into discrete probability is calculating chances like this. Okay. And what is the time right now? It's 41. We got about 9 more minutes. So I'll give you another example. This one doesn't really involve money, but it's kind of fun anyway. So let's say we have a class. My assembly language class is pretty big. I have 50 plus students in that class. So I want to know, what are the chances that at least 2 people in my class share the same birthday? This is called, typically, this is really literally called the birthday problem. So what do you think? What do you think would be the chances of at least 2 people having the same birthday in a class of 50? Most people think it is about, oh, let me see, there are 365 days in a year. 50 is sort of 1/7 of it. So maybe 1 divided by 7, maybe that's the chance of having at least two people, at least 2 people having the same birthday, or something along that line. No, the chances are much higher than people expect. Okay? Nope, it's not that. It is much higher than what people expect. Um, because what you do is you just have to say, let's take away the chances of everybody having a unique birthday. As it turns out, the chances of everybody having a unique birthday when you have a class of 50 is actually pretty low. It's lower than most people think. Okay, it's not intuitive. All right, so I can get you to okay, let's work on the math here a little bit. Okay, so let's calculate the chances. And let me use my tablet this time. Let me switch the screen to the tablet. And now we are talking a little bit about the birthday problem. So we got 365 days in a year, and then we have a class of 50 people. And what I'm trying to do is to say I need to have I need to know the chances of everybody in the class, each one of the 50 people, having a unique birthday, because that would be the complement, the opposite of at least two people in this class sharing a birthday. Does that make sense? All right, cool. All right, so in that case, ordering is important. Okay, let me see. Is ordering important? The first person, okay, yes, ordering is important. So we have 50 people, and let's just say this is student one, all the way up to student 50. So student one, basically say, okay, I can choose any one of the 365 days. 365. Student two says, okay, I only have 364 days to choose from because the first person chose one day already. 364, 363, blah blah blah, and all the way down to the 50th person. It's going to be 365 minus what, 49. Okay, so, and then you have to multiply all of these numbers together, which is going to be a gigantic number. Okay, this number is going to be pretty large. This is the permutation of choosing 50 out of 365. So let me switch to my spreadsheet here. So in a spreadsheet, you can say permutation, permut, and you are looking at the total number of elements, which are 365. There are 365 days in a year, and we are choosing 50 of those 365 days. And ordering is important in this case because which person has which day is significant. So that's a pretty huge number. Then you go like, what are we going to do with this number here? So now you have to look at this, which is how many ways can we assign 50 unique dates from 365 choices to begin with. So now you look at this and go like, what if there's no restriction, right? What if each person can choose any one of the 365 days in a year? So how many ways can we arrange that? Okay, there's no restriction whatsoever. The first person can choose any one of the 365 days. The second person can choose any one of the 365 days, and so on. So that number is very easy to calculate because it would be 365 to the power of 50, because the choice of each person is independent to what other people have chosen already. So it's just a straight up multiplication. So that number is pretty gigantic as well. So now you want to divide these two because that would give you the probability. So now we take this count and then divide it by this count over here, and here's a number. Okay, it's 0.2. Okay, 0.02. Then the question is, what is that representing? This is representing the probability of everybody having a unique birthday when you have a class of 50 people. Let me say that one more time because I think some of you are not believing this. The chances of everybody in the class of 50 having a unique birthday, no two people in the class have the same birthday, is 0.029. Basically 3%. You have a 3% chance that everybody has a different birthday in a class of 50. And Amon is correct. So this boils down to the opposite, which is the complement, which is basically just 1 minus this number here, would be the chances of at least two people in a class of 50 sharing the same birthday. It's a 97% chance. I wouldn't call that a certainty, but I would call that a pretty high probability. Isn't that interesting? I mean, obviously I think it is interesting, but I think most people do not find this intuitive. Exactly. So this is the kind of stuff that we are getting into now, is to calculate probabilities. Now it is discrete probability, which means we are not going to step on your certain concepts in your statistics class, which deals with a normal distribution. So we are not going to deal with normal distribution. We're not going to deal with standard deviation. We're not going to deal with variance and that sort of stuff. But we are going to deal with things that are kind of interesting in its own way. Okay, for instance, if you know the probability of a bit not transmitting correctly over a Wi-Fi network, okay, and you know the size of a packet that you need to send, out of the size of a UDP packet that you have to send because you're gaming. How do you calculate the chances of the packet not being able to send correctly? So you have to resend that packet, which impacts the lag time of your League of Legends game. Don't you think that's a very important number to understand? I think it's a very important number because you really want to know what is my expected lag time when I'm playing these video games. Oh, okay. If you think that genre is bad when it comes to lag time, you can also try CS:GO. The shoot 'em up games. Because people buy these, super expensive monitors that has a refresh rate of what is the refresh rate of a gaming monitor these days? 200 hertz or something like that. 144 hertz. I mean, the human eye has a natural refresh rate of about 20 frames per second. So even if you were to double that, it would just give you like 60 hertz. Should be plenty fast enough for the human eye. 144 hertz is it's a little bit faster than what people can really perceive. Now, on the other hand, if you are a fly, as in the insect, if you are a fly, a normal fluorescent light is going to be on and then off, and then on and then off, because the natural refresh rate of the eyes of a fly is insanely high. So that's why you can never really hit a fly using your hand. If you don't use a tool, it becomes very hard to swat a fly because it can see your hand coming basically in slow motion. It's kind of like the Matrix in slow motion. The fly just sees your hand. I think I'm going to finish this slurp before I start to fly. Yep, now would be a good time to start flying. That's basically what a fly is seeing when you're trying to swat it. Yep, very interesting stuff, when you get into the animal kingdom. All right, yes, I totally digressed. And it's also the time. It's also time to end today's lecture. So next week we're gonna go into discrete probability full bore. Okay, which means this long weekend is a good time for you guys to read ahead of the class, at least by one module. Okay, just kind of get into the module, get some understanding of the terms, and then on next Monday we'll get into those terms. Okay, because we have to define the terms first. What is an event? Okay, what is a sequence of events? What is the set of outcomes, and so on and so forth. So there are some really tricky stuff too. Let me just, I know it's time to end today's lecture, but I do want to point out certain things that are a little bit interesting. So even though it's just called counting, which you think, hey, I know counting, I've been knowing this for 20 years, 30 years, or something like that. But when we get to some of the calculations, look at these things. Look at this. Okay, what is this? Right? And what is that? So yes, so we are actually, doing recursive definitions in order to generate a set of all possible outcomes. And it does involve, really awkward, strange symbols and notations that resemble certain things that we have already talked about, but then it's like, well, how does it relate to some of the other stuff, right? What is this symbol representing? So go ahead and read ahead of the class because you're gonna need it. Um, Other than that, I got nothing else to say for this lecture. Um, Somebody is typing in the text channel, so I'm gonna wait until Armand is done typing here before I stop the live stream. Oh, nothing. Okay. I thought he's typing to justify the 114 hertz refresh rate of the monitor. Alrighty. I will see you guys on Monday. Have a nice weekend, but please read ahead of me because it would really help in this case. Alrighty. Have a nice weekend, and I'll see you on Monday.